Hello grade 12s and welcome to this lesson on exponential functions. An exponential function is a function in which the variable is an exponent. For example, y is equal to a to the power x. Let us join Omashni as she explores the exponential function in more detail.
Let's start by plotting the graph for y equals 2 to the x. To do that, we are going to work out some values for the x and the y. Let's put them into a table. For the x value, we'll use -3, -2, -1, 0, 1, 2, and 3. That should be enough values to show us the shape of the graph. To find the y values, we use the formula y equals 2 to the x for each x value. For x equals to 1, 2 to the power of 1 is just 2. So the y value here is 2. 2 squared is 4, and 2 cubed is 8. Now what about 2 to the power of 0? I have a quick way to explain what 2 to the 0 is. What is 2 cubed divided by 2 cubed? Any number divided by itself is 1. But using the rule of exponents, when you divide two numbers with the same bases, you can subtract their powers. 3 minus 3 is 0. So we get 2 to the power of 0. That must mean that 1 equals 2 to the 0. It is useful to remember that any number to the power of 0 is 1. For our exponential functions, we don't use b values of 0 or less. Now, what value will we get for y when x is -1? So y is 2 to the power of -1. Again, you should remember your exponential laws. A number to a negative power is the same as 1 divided by that number to a positive power. Let me give you an example. What is the answer to 2 cubed divided by 2 to the power of 4? Well, 2 cubed is 8, and 2 to the 4 is 16. So we get an answer of half. But we could also do this calculation another way. To divide exponents that have the same bases, we can subtract their exponents. 3 minus 4 is -1. So the answer is 2 to the power of -1. So 2 to the -1 must equal a half. So this base to the power of -1 is equal to 1 divided by the same base to the power of +1. 2 to the -2 is equal to 1 divided by 2 squared. So that's a quarter. And 2 to the -3 is 1 divided by 2 cubed. That's 1/8. Now let's plot these points and see what the graph looks like. First we have -3, an eighth here. Then -2, a quarter. Next is -1, a half. Then 0, 1 here, followed by 1, 2, then 2, 4, then 3, 8. Can you see the shape of the graph from these points? We can see the shape enough to join the points. If we tested some points in between these ones, we would find that the graph curves like this. But the graph doesn't stop at these points. Let's look at what happens to the graph after the point 3, 8. What happens when x is 4? Well, y is 2 to the power of 4, so that's 16. And for x equal to 5, y is 32. For x equal to 6, y is 64. That's way off the graph. So as x increases, y increases exponentially. That means y increases more rapidly than x. We could put an arrow onto the end of the graph here to show that it continues to infinity. Now let's have a look at the negative x values that we have on the graph. their y values are all fractions between 0 and 1. So where do you think the point for x equals -4 will be? Let's check. Y equals 2 to the -4, which is 1 divided by 2 to the 4. That's 1/16. So the point is still positive, but closer to the x-axis. As x decreases, when do you think the y value will go below the x-axis? This is what makes this graph interesting. The y value can't ever reach a value of 0, never mind go below the x-axis. For example, if x is -10,000, y will still be a very small positive fraction greater than 0. So as the x values decrease, the y values get closer and closer to 0 without ever reaching 0. We can show this with an arrow on the graph. So the graph will move closer and closer to the x-axis, but will never intersect it. We say that the y equals 0 is an asymptote for the function y equal to 2 to the power of x, and y equals 0 everywhere on the x-axis. So the graph can never have a point that is on the x-axis. So here is our complete graph for y equals 2 to the power of x. Can you describe some of the characteristics of this graph? What is the domain, the set of possible x values of this graph? What is the range, the set of possible y values for this graph? What are the graph's maximum and minimum values? What are the x and the y intercepts? Let's start with the domain. X can be any number right from -infinity to +infinity. There are no restrictions on the domain of this graph. Then the range. The y value can't be 0 and it can't go below 0. On the positive side, y can go to infinity. So we can write the range as round bracket 0 to round bracket +infinity. Now what about the maximum values? There is no maximum that we can write down as a value when a graph goes to infinity. Would you say that the minimum value is 0? Well, 0 is not actually on the graph, so it can't be a minimum value. The graph decreases infinitely towards the x-axis, so we don't have a minimum value for this graph. Right. What about the x-intercepts? A graph that has the x-axis as an asymptote won't have any x-intercepts. What about the y-intercepts? This graph intercepts the y-axis at the point 0, 1. So far, we've only looked at one exponential function, y equals 2 to the x. Now we are ready to change the base b of this function to other values. Let's choose to make b equal to 4. I will leave you to plot this graph for yourself using a table of values. This is the graph you should find. The graph of y equals 4 to the power of x. If we compare this graph with the graph for y equals 2 to the x, the graph with a base of 4 is steeper than the graph with a base of 2 because the y values are increasing more rapidly. The graphs both go through the point 0, 1, and they have the same y-intercept. Why do you think this happens? Think about the x value on the y-axis. It is 0. Any number to the power of 0 is always equal to 1. So any exponential graph of the form y equals b to the x will cut the y-axis at 0, 1. For the negative x values, both graphs approach the x-axis without ever reaching it. So they have smaller and smaller positive y values that are close to 0. Here is another graph. How would you work out what the formula of this graph is? The easiest way to find the formula of this graph is to read off the coordinates of some points on the graph. This point is -1, a third. This point is 0, 1. Here is 1, 3, then 2, 9 here, and 3, 27 here. Do you see a pattern in the coordinates of these points? Look at the y value. It increases from a third to 1, then to 3, then 9, then 27. How could we describe this pattern? We are multiplying by 3 each time. Here, 3 times 3 is 9, and that's 3 squared. 9 times 3 is 27. We can write that as 3 cubed. So the base of the exponent we are working with is 3. The function for this graph will be y equal to 3 to the power of x. So far, we have only used b values that are positive natural numbers that are greater than 1. What do you think the exponential graphs will look like if the b is a positive fraction less than 1? Let's draw the graph for one value to see what it looks like. Let's choose a base value between 0 and 1. Let's make b equal to a half. The equation then becomes y is equal to a half to the power of x. To see what happens to this graph, let's work out some values for x and y. If we add them to the table we used for y equals 2 to the x, then we can compare these two functions with each other. For our calculations, it will help to write a half as 2 to the power of -1. So we get y equals 2 to the power of -x. Let's start here with x equal to -3. Y will be 2 to the positive 3, that's 8. When x is -2, y will be 2 squared, and that's 4. For x equal to -1, y is just 2. Then 2 to the 0 is always 1. For x equal to 1, we can use this form of the equation again. A half to the power of 1 is a half. A half to the power of 2 is 1 divided by 4, which is a quarter. Then for x equal to 3, a half to the power of 3 is 1/8. Now compare these y values with the y values for y equals 2 to the x. 1/8 is the inverse of 8. A quarter is the inverse of 4. Do you see that for each x value in the table, the two y values are the inverse of each other? So the y values for y equal to a half to the power of x are the inverses of the y values for y equal to 2 to the power of x. As x increases, the y values of 2 to the x increase, but the y values of a half to the x decrease. Can you use these points in the table to predict what the graph will look like? I'm sure you've seen that the graph will be some kind of reflection of the graph of y equals 2 to the x. Let's plot the points and see. Watch what happens as we plot the points. -3, 8. -2, 4. -1, 2. 0, 1. 1, a half. 2, a quarter. 3 and 8 is about here. We can join the points with a smooth curve, and we can put arrows onto the ends of the graph, here. It is the same as the graph for y equal to 2 to the power x. It's just that the one curves down this way, and the other curves down that way. It is a reflection of the graph of y equals 2 to the x. Can you see what the line of symmetry or the mirror line for this reflection is? Have a look at this animation. Watch how the graph is reflected about the y-axis. In the same way, the graph of y equal to a third to the x is a reflection about the y-axis of y equal to 3 to the x. and the graph of y equal to a quarter to the x is a reflection about the y-axis of y equal to 4 to the x. Can you find a way to describe in general terms what we have found here? How can we describe the relationship between a graph for y equals b to the x and the graph for y equals the inverse of b to the x? We can say that for any exponential function of the form y equals b to the x, if we invert the base of the function, then the graph of the new exponential function will be the reflection about the y-axis of the original one. So far, we've looked at different exponential graphs that are all of the form y equals b to the power of x. But we haven't defined any of these functions as the parent graph for y equals a times b to the power of x plus q. In fact, all of the graphs we've looked at today had an a value of 1 and a q value of 0. So in a way, all of these graphs are parent graphs. The problem is that there isn't just one graph that represents y equals b to the power of x. Fortunately, the base for the graph will always be given, and for each b value, there is a whole family of exponential functions. So for each given b value greater than 0, we can change the a value and the q value of the formula to see what effect this has on the graph. There is one value of b that is different from the others. b equals 1 produces a different graph from any other b value. The formula is y equals 1 to the power of x. But 1 to any power is still just 1. So the graph is the graph of y equals 1. That's a horizontal line here on the graph.
Thank you for joining us, grade 12s. Remember to do the questions found in the exponential and logarithmic functions task video. You will also learn more on exponents on our website www.mindset.co.za/learn. Goodbye.